In this episode, we want to explore how neural networks learn to handle sequences through recurrent models like RNNs and LSTMs, and eventually through the powerful idea of attention.
It's a really incredible journey when you look at it. It charts the whole path from these, inherently limited models with short-term memory problems to the huge systems we have today.
The ones that process language on a global scale.
Exactly. And for anyone who wants to get a real grip on modern large language models, this evolution is, well, it's the critical backstory. You have to know it.
Absolutely. The new systems are amazing, but they are definitely standing on the shoulders of these earlier ideas. So I think we have to start with that first fundamental problem. Why did the simple neural networks we were using, the feed-forward models, just completely fall apart when they had to deal with data that had an order?
Well, those simple feed-forward networks are built for static tasks. Think about classifying a photo.
Okay, like cat or dog.
Right. All the pixels are there at once, and the network just judges the whole image. But sequence data text, speech, financial data, even sensor data from a car, it's completely different.
Because the meaning of what's happening now depends on what happened before.
Exactly. The meaning of the word you're on or the current stock price is inseparable from what came before it.
Context is everything. I mean, if I'm reading a sentence and I hit the word bank, I need the previous words to know if we're talking about a river or a financial institution.
And a feed-forward network just can't do that. It treats the word bank completely on its own, ignoring all that rich context.
It processes X1, then X2, then X3, but it just throws away the calculation for X1 before it even looks at X2.
Right. It lacks any mechanism to pass a summary of what it's seen forward in time, so it's basically blind to temporal dependencies.
So we needed a kind of network memory. Where did that idea of making a network recurrent, of creating that internal loop even come from? Was it just a computer science idea?
Not at all, actually. It has much deeper historical roots. The earliest theoretical models weren't based on silicon chips. They were inspired by biological neuroanatomy.
So from the brain.
Yeah, researchers in the 70s and 80s were looking at systems based on something called coupled delay differential equations, or DDEs.
Delay differential equations. That sounds like a way to describe signals that take time to travel through a system.
That is precisely the idea. They were trying to mathematically model these continuous time neural processes, acknowledging that communication between neurons isn't instant.
There's a delay.
There's a delay, and the current state of one neuron depends on a previous delayed state of another. So these DDEs became a way to bridge ideas from neurophysiology and signal processing.
Okay, so if the theory started in continuous time, like a smooth flowing signal, how did we end up with the discrete step-by-step models we use today, like the RNN?
It was through a process of sampling and discretization. You basically take that continuous process and you sample it at regular intervals.
You chop it up into steps.
You chop it up, and that converts those smooth dynamics into the step-by-step calculations that we can actually run in code.
That history really grounds the architecture. It shows it's not just some arbitrary loop someone came up with, but a purposeful adaptation of a dynamic system.
Yeah, it is.
And to train a network that has this loop, standard gradient descent, isn't enough, is it? We need a way to trace an error backwards, but through time itself.
And that's where backpropagation through time, or BPTT, becomes absolutely crucial. Regular backpropagation calculates the gradient, the instructions for how to adjust the weights by moving backward through the layers.
Right.
DPTT is the adaptation for these recurrent systems.
Because an error you see at step 10 might have actually been caused by a mistake way back at step 1.
Correct. When you unroll the network, which we can get into, you basically treat it like a very, very deep feed-forward network where each time step is a new layer.
But they all share the same weights.
They all share the same weights. And BPTT uses the chain rule to sum up the error's contribution across every single one of those time steps. It's how the system learns temporal connections, not just spatial ones.
Okay, so let's unpack that core architecture.
Right.
The basic recurrent neural network, the RNN. What's the simple intuition behind how it passes information forward?
The central idea is what we call the state loop. Just imagine a single little computational cell. At any given step, let's say step t, it takes two things. The new input, x sub t.
The next word in the sentence.
The next word, exactly. And it also takes the output from its own calculation at the previous step. We call that the hidden state.
So it's getting new information and its own old memory.
Yes. It processes those two things together to produce a new output, and this is the critical part, it also calculates a new hidden state to pass along to the next step.
So that hidden state is like a constantly updated summary, A little packet of memory about everything the network has seen so far.
That's a perfect way to put it. It's the network's short-term memory packet. After the first word, it's a summary of just that word. After the 10th word, it's a summary of all 10 words, all blended together.
And that simple feedback loop is what lets it model dependencies.
It is.
But when we look at diagrams, we see that loop. For actual computation, though, you mentioned unrolling it. Why is that necessary for training?
The training process needs to calculate those gradients with BPTT across the whole sequence. So unrolling is really a computational trick that lets us do that. We take that single looping cell and we just visualize it as a long chain.
One cell for each word in the sentence.
One for each word. For a 10-word sentence, you have 10 connected cells, but they all share the exact same set of weights.
So you're turning a dependency in time into a dependency in space. You're approximating the real loop with a long chain.
Precisely. You're treating the whole sequence like a series of what are called finite impulse response, or FIR, sequences. Instead of this infinitely looping system, you have a finite, manageable chain.
That seems like a smart way to handle it, but you mentioned there's a big catch. That unrolling introduces what you call artificial discontinuities, because you have to cut off the sequence at some point. How does that affect what the model can learn?
You've hit on the critical trade-off. I mean, in theory, the context for a word could go back indefinitely.
The beginning of the book.
To the beginning of the book. But in practice, we have to set a limit, say 50 steps, just to make BPTT computationally possible. And by forcing it to stop, you're creating an artificial boundary.
So if some crucial piece of information for step 51 was way back at step 1, the network just completely misses it because the window closed.
Yes, and this leads to a really interesting theoretical point. There's a parallel to the sampling theorem in signal processing, and it basically says that this unrolling trick only really works well if the sequence can be reasonably treated as a collection of independent chunks.
Okay, so if the text naturally breaks down into paragraphs, or a stock market chart has short, self-contained movements, then cutting off the window isn't so bad.
Exactly. If the context from the really distant past is less critical anyway, then the truncation doesn't hurt as much.
And if that assumption holds true, you get this huge computational win. You can process these chunks in any order or in small batches.
Which is how we structure training data for RNNs. But, and this is the big but, if the dependency is truly long range, this whole approximation just fails.
And that failure to capture long-range dependencies is the Achilles heel of the basic RNN. It leads us straight to the famous or infamous vanishing gradient problem.
It is the fundamental flaw.
So even if the network conceptually carries that little memory packet, the process for learning how to use it just breaks down over time.
Completely. RNNs are fine for very short sequences, maybe 5-10 steps, but they just catastrophically fail to connect cause and effect when there's any real distance between them. They forget.
Okay, let's get into the weeds a bit on why that happens. We said the error signal has to travel backward through all those steps in the unrolled chain. Why does that signal just vanish?
It's a direct consequence of using the chain rule over and over again in BPTT. The total update for a weight early in the sequence involves multiplying the local gradients from every single step between the error and that weight.
So if you have 100 steps, you're multiplying 100 numbers together.
100 numbers. And the size of those numbers is heavily influenced by the activation function, like 10 or sigmoid, which were standard in RNNs.
And those functions, their derivatives are mostly small, right? They're less than 1.
Right. The derivatives are small pretty much everywhere except right near the origin. So as you propagate that signal backward, if at each step you're multiplying by, say, 0.5.
And you do that 100 times.
That number gets incredibly close to 0, incredibly fast. It vanishes.
So the weights at the beginning of the sentence get basically no update signal. No learning happens.
The network literally stops learning the connection between the start of the sentence and the end of it. The technical term is that the Jacobian matrix becomes numerically singular. The system just can't figure out the necessary weight changes.
It sounds like a complete dead end, which of course demanded a totally new architecture. And that brings us to the long short-term memory network, the LSTM.
Right.
What was the big insight there? How did LSTMs solve this vanishing gradient problem so effectively?
The core idea was to build in mechanisms, these gates, that are actually trained to keep the gradient of magnitude close to 1 as it flows backward. LSTMs were explicitly designed to be robust against this vanishing effect.
So instead of the signal just uncontrollably shrinking, the network learns to actively protect and preserve the information it thinks is important.
That's the intuition perfectly. The key innovation is making a distinction between the hidden state, which is the short-term output, and a new thing called the internal cell state.
The memory cell.
The memory cell. You can think of it like a master conveyor belt of information that runs straight through the entire sequence. And crucially, the updates to this cell state are mostly linear, which is the mathematical key to preventing the gradients from vanishing.
So let's talk about those gates. How do they actually control the information on this memory conveyor belt?
There are three main gates, and they all use the sigmoid activation function.
Because sigmoid squashes everything to be between 0 and 1.
Exactly. So it acts like a little dial or a switch. 0 means block everything, and 1 means let everything pass through.
Okay, so the first one is the forget gate. What's its job?
The forget gate looks at the new input and the previous hidden state, and it decides what information from the old cell state is no longer relevant and should be thrown out.
So if a sentence starts with, the cat sat on the mat, and then switches to the dog chased a ball, the forget gate learns to zero out the cat and mat information.
Precisely. It learns to forget context that's become stale. Then you have the input gate.
Which decides what new information to let in.
Right. It decides what new stuff from the current input is worth storing. And it works with another component that calculates the actual new information, usually using a hyperbolic tangent, or tan, function.
Why tan for that part?
Tan is really important here. It's what we'd call a data warping function. It bounds the data between -1 and +1.
So it stops the numbers inside the cell from getting ridiculously big.
It stops them from exploding, which would be the opposite problem, exploding gradients. It keeps the internal signal well conditioned.
So the input gate decides how much of that new bounded information to add to the conveyor belt.
Correct. And the final update to the cell state is just a combination of those two things. You take the old state, multiplied by the forget gate's decision, and you add the new information, multiplied by the input gate's decision.
It's an addition, not a long chain of multiplications.
And that's the key. That additive interaction protects the gradient. It can flow back through hundreds of steps without disappearing.
And there's one more gate, right? The output gate.
Yes, the output gate. It decides what part of the new updated cell state should be revealed as the visible hidden state for the next step. So the cell state might hold all this rich information, but the output gate decides what the network actually shows to the outside world.
So it's actively deciding what to observe and what to keep hidden for later.
It is. It's a very complex but stable system.
And that architecture just completely changed the game. LSTMs became the engine for the first really high-performing systems in speech recognition, and maybe most importantly, they enabled the encoder-decoder architecture.
The sequence-to-sequence, or seq-to-sec models, that was a massive leap.
Because for the first time, you could map an input of any length to an output of any length.
Right. Before LSTMs made that possible, you were stuck with fixed-size inputs and outputs, which is totally impractical for something like machine translation.
A German sentence isn't the same length as its English translation.
Almost never. The encoder LSTM would read the whole German sentence and compress it down into one context vector, and then the decoder LSTM would take that vector and generate the English sentence word by word.
It was incredibly powerful, and it's probably worth mentioning the gated recurrent unit, or GRU, here as well.
Yeah, the GRU came along a bit later. It basically takes the same core idea of gating and memory control, but simplifies the architecture. It merges the hidden state and the cell state and cuts the number of gates down to 2.
So it's often faster to train, needs a bit less data, and became really popular for practical applications.
Exactly. It still solved the long-range dependency problem much, much better than a plain RNN.
So LSTMs and GRUs largely fixed the memory problem. But that brings us to the next big roadblock. If they were so good at remembering, why did we have to move on from recurrence altogether? What was the hard limit that even these sophisticated gates couldn't fix?
The answer is parallelization.
And the rise of GPUs.
Exactly. The fundamental limit wasn't about memory quality anymore. It was a structural problem baked into the very definition of recurrence. To calculate the state for step T, you absolutely must have the result from step T1.
It's sequential by its very nature. There's just no way around it.
No way around it. And that completely crippled training efficiency on modern hardware. GPUs are designed to do thousands of calculations all at the same time, in parallel.
But with an LSTM, you can't calculate the end of the sentence until you've finished calculating the beginning.
Right. So training on a whole book or a really long financial time series became painfully slow. The speed was literally capped by the sequential nature of time in the data.
The structural bottleneck. It sounds like it demanded a totally new way of thinking. a way to process every single token in the input at the same time.
It did. It required a complete paradigm shift.
And that shift leads us to the concept of attention. Now, it feels like this idea just appeared out of nowhere, but it actually started as a fix for the RNN models themselves, right?
That's a key point. Attention didn't start by trying to replace recurrence. It was introduced as a patch, a very clever patch, for that C2-sec RNN model we were just talking about.
For the bottleneck problem.
Exactly. Remember how the encoder LSTM had to cram the entire meaning of the input sentence, no matter how long, into one single fixed-size vector?
Which seems impossible for a really long sentence.
It was. That single vector was a huge information bottleneck. The model would just lose all the nuance and detail, and the translations for long sentences were not great.
So the first attention mechanisms were designed to let the decoder peek back at the original input.
It let the decoder look back at all the words in the source sentence at every step of generating the translation. It was an active searching mechanism. It could dynamically decide where to focus.
So when it's generating the fifth English word, it doesn't just look at that one context vector. It calculates which of the German words are most relevant for this specific step.
And it aggregates context only from those relevant parts.
That's so intuitive. But how does it work mathematically? How does a network focus on relevance without going step by step?
The mechanism is defined by three roles: the query, the key, and the value.
Q, K, and V.
Q, K, and V. So imagine you're the decoder trying to produce a word. Your current state is the query vector. It's like you're asking a question. And every word in the input sentence is a potential source of information. Each of those words has a key vector and a value vector.
So my query gets compared to every single key.
Yes. The network computes a similarity score, usually with a dot product, between your query and every available key. That score is a relevance weight. A high score means that input word is really relevant to your current question.
And once you have all those weights, you use them to combine the content.
You use those weights to calculate a weighted average of all the value vectors. The values are the actual content. So the final output is this new vector where the most relevant input words contributed the most and the irrelevant ones contributed almost nothing.
Which lets the model skip the whole sequential process and just directly access global context instantly.
And that's what unlocked the massive potential for parallelization. But what's fascinating is that you can actually formulate this attention mechanism itself as a type of recurrent neural network.
Wait, how does that work if the whole point was to get away from recurrence?
It's a bit of a counterintuitive mathematical insight. The calculation for attention involves a summation over all the input tokens. And if you compute that sum iteratively, one token at a time, it actually takes on the mathematical form of a many-to-one RNN cell.
So if you built it that way, wouldn't it just run into the same old vanishing gradient problems?
If you did it naively, yes. But this insight led to really clever innovations, like something called the RNN module.
Attention as a recurrent neural network.
Right. RNN is designed to be super efficient. It uses advanced algorithms, specifically something called the parallel prefix scan, to compute the rolling sums in the attention calculation.
A parallel prefix scan. So that's a clever way to do a sequential-looking calculation in a parallel way.
It's a trick to do it in logarithmic time instead of linear time, which means RNN gets the best of both worlds. It can leverage GPU parallelism during training, just like a transformer.
But it acts like an RNN during inference when you're actually using it.
Exactly. For predicting the next step, RNN only needs constant memory for new tokens. You don't have to reread the entire history every single time a new data point comes in.
Which is incredibly efficient for streaming data, like in time series forecasting or reinforcement learning.
It's proven to be very effective in those areas. It gets performance that's comparable to full transformers on things like weather prediction, but with the memory efficiency of a classic RNN.
But the real turning point, the moment that overthrew recurrence for almost everything else, was that 2017 paper, Attention is All You Need. What made the transformer architecture so different?
The transformer just made this incredibly bold move. It completely abandoned recurrence. No LSTMs, no GRUs, nothing. The entire model was built purely from attention mechanisms and some standard feed-forward layers.
And by ripping out recurrence, they removed that last sequential bottleneck.
Every single calculation could now happen at the same time, across the entire sequence. The efficiency gains were just revolutionary. Training times dropped dramatically compared to LSTMs, which allowed people to start training much, much bigger models.
The transformer also introduced a crucial idea for making this work: self-attention. Before, the decoder's query looked at the encoder's keys. In a transformer, where do the query keys and values all come from?
In self-attention, they all come from the exact same input sequence. The tokens are attending to themselves.
What does that mean?
It means when the model is processing, say, the fifth word in a sentence, that fifth word acts as the query, and it looks back and compares itself to the key and value vectors of all the other words in that same sentence.
So it builds this incredibly rich map of how every word relates to every other word directly instead of through a blended sequential memory.
Yes, but this created a new problem, a critical one. By getting rid of recurrence, the model lost all sense of order. If you just shuffle the words in a sentence, a standard attention mechanism will give you the exact same result. It only sees relationships, not positions.
So dog bites man and man bites dog would look identical to it.
They would, which is obviously a huge problem. This is why they had to introduce positional encoding.
They needed a way to manually inject the order information back into the data.
That's right. Before the word embeddings go into the transformer, you add another vector to them, a vector that just encodes the absolute position of that token in the sequence. It's often done with sine and cosine functions.
So you're explicitly telling the model, this is word number 1, this is word number 2, and so on.
And that allows the model to use sequence information within its parallel global context calculations. It was a brilliant fix.
Another key part of this was multi-head attention. Why not just use one big attention mechanism? Why split it up into multiple heads?
Because a single attention mechanism can only learn to calculate one type of relevance. Multi-head attention lets the model analyze relationships from many different perspectives at the same time.
So it's like having a team of different specialists all looking at the same sentence.
That's a perfect analogy. Each attention head has its own set of query, key, and value matrices. And because they're all trained independently, each head learns to focus on a different kind of relationship.
So one head might learn to track syntax, like which verb goes with which noun.
And another head might track something completely different, like making sure a pronoun like it refers back to the correct object from 3 sentences ago.
And then you combine the findings of all these specialists.
You concatenate their outputs and blend them together. It creates a final contextual representation for each token that is unbelievably rich and flexible.
This whole journey, from the forgetful RNN to the stable LSTM, and then to the parallel power of attention. This is the direct line to the AI we have today. What was the immediate real-world impact, like in machine translation?
The impact on neural machine translation, or NMT, was huge and immediate. People saw these large progressive gains improvements of 2 to 3 points on the BLEU score, which is a standard metric. That's a massive jump.
And what did that mean for the actual quality of the translations?
One of the biggest improvements was in aligning rare words. You know, when a proper noun or some very unusual word comes up, the old RNN models would often lose track of it in that compressed context vector.
But with attention.
With attention, the decoder could look back, find that specific rare word in the input, and make sure it got translated correctly. The fidelity just shot up.
And we see these models everywhere now, not just in language. What about in time series data and operational systems?
Time series is a massive area. Forecasting energy demand, predicting weather, financial fraud detection, these are all sequence problems.
And models like that RNN module you mentioned, they can look at much longer histories now without the huge computational cost.
Exactly. RNN can give you the quality of a full transformer, but with the inference efficiency of an RNN, which is perfect for tasks where new data is constantly streaming in and you need instant updates.
That distinction between training in parallel and having efficient inference is so important for actually deploying these things. What about in interactive settings, like robotics?
Sequence models are becoming central to reinforcement learning. An agent's entire interaction with its environment, every observation, action, and reward is a sequence.
So the model needs to understand that whole history to decide on the best next move.
And models like decision transformers do exactly that. Instead of just learning a policy from rewards, they treat the entire history of states, actions, and rewards as one long sequence, like a sentence. They learn to model the sequence of actions that leads to high rewards.
So they're modeling successful behavior directly.
Which is a really powerful way to train complex systems, from robotics to traffic control.
It really feels like every time the field hit a wall, first the memory problem, then the parallelization problem, a new architecture emerged to just knock it down.
That really is the story of this evolution. The RNN gave us the idea of recurrence. The LSTM gave us the fix for memory. But it was then attention, fully realized in the transformer that gave us the speed and the global context needed for the massive scale of modern AI.
And that transition from a step-by-step temporal process to a total parallel awareness of context, that's what set the stage for everything that came next. Next time, we can really get into the weeds of the transformer itself and see how models like BERT and GPT use this purely attention-based world to do what they do.
The ability to model relationships in parallel, and crucially in both directions, understanding a word based on what comes before and after it, was the final ingredient. That led directly to the contextual embeddings that define modern NLP.
It leaves you with a really interesting thought. If attention solved the sequential problem by taking time out, and then positional encoding had to be added to put time back in, maybe the future is about finding even smarter ways to encode the relative position and flow of time, not just the absolute position. That's a huge question for the people building the next generation of these models.
Thanks for listening to the Adaptus podcast. If you have any questions, feel free to reach.